now we're dealing with the ideal gas law. Very exciting. I do find it kind of humorous. They have a kid under nitrous oxide, I assume, and their mouth being worked on. So, it is a gas, also known as laughing gas. Okay. So, the ideal gas law. I get distracted easily. I apologize. So, the learning goal is use the ideal gas law equation to solve for pressure, volume, temperature, or moles of a gas when given 3 of the 4 variables in the ideal gas law equation. So we can calculate the density, molar mass, or volume of a gas in a chemical reaction so we can know what the output is going to be. All right, so the ideal gas law is a combination of 4 properties: pressure, volume, moles, and temperature, written as a single expression. PV, pressure and volume, is equal to moles, R, and temperature. Now we got to go, okay, what is R? That is our gas law constant, okay? So that is something that will never change in this equation. So R, all right, you can see how they're like PV over NT equals R. So 1 atmosphere times 22.4 liters. Remember, we know these are constants, okay? Because 1 mole is equal to that, and 1 atmosphere is equal to that. That is going to give us our liters per mole Kelvin, okay? Liters in atmosphere per moles Kelvin, okay? And that constant is 0.0821, okay? 0.0821. So R here is always going to be equal to 0.0821 liters of atmosphere per moles Kelvin, all right? Again, if I'm taking notes, things I want to know, things I want to have jotted down. All right, so using different units for pressure, 760 millimeters of mercury gives us another value for R, 62.4 liters of millimeters per mercury per mole Kelvin. I said that wrong. 62 liters millimeters of mercury per moles Kelvin, okay? So, again, equation, all they did is change atmospheres to torrs, and voila, here's our constant. So we really want to know what we're working with. Now, can we go back and forth? Sure. But if we have constant and we're dealing with liters at atmosphere, well, we'll use a constant of 0.0821 liters, okay? And if we're doing instead torr or millimeters of mercury, we use 62.4, all right? Doesn't matter, they're equivalent to one another, but it matters in the sense that you need to keep track of what you're working with. So, how to use the ideal gas law? State the given and needed quantities, organization. We then rearrange the ideal gas law equation to solve for the needed quantity. Okay, we set up our formula. Then we substitute the gas data into the equation and calculate the needed quantity. Plug and chug, okay? Organization, isolation, and then plug and chug, all right? Those are the 3 things. Simple as that. So, how many moles of nitrogen gas are present if the sample occupies 215 milliliters, 0.25 liters, at 0.813 atmospheres at 30 degrees Celsius? All right, well, do we have enough information here? Okay, well, let's see. We've got volume, we've got pressure, we've got temperature, and then we're looking for moles, all right? And we know our constant. And since we're using atmosphere, what constant are we going to use? The atmospheric constant. So let's state our quantities. So our pressure, 0.813 atmosphere. Volume, 0.215 liters. Moles, we don't know, but we're going to find out. Our constant, we're using atmosphere here, so we use atmosphere here. So 0.0821. And then we got to get our temperature in Kelvin, always in Kelvin, because that's what we do. That's how we roll. Take 30 degrees plus 273, 303 degrees Kelvin. Awesome. We've got all the data we need. We've got our chart filled out. Now we've got to rearrange our formula to solve for moles. Okay, so rearrange the ideal gas law equation to solve for the needed quantity. Well, in this case, check it out right here. Now, if we go back, where are we going back to? Right here. PV equals nRT. Well, how did they get N alone? Because we're looking for N. They simply divided both sides by R and T. Divide this side by R and T. On this side, what's going to happen? Gone, leaving N by itself. So let's see if that algebra worked. All right. Boom, PV over RT. Look at that, and N is alone. Algebra takes you everywhere. People are like, I've never used algebra any time in my life. You use algebra every day, you just don't realize it. Remember, I'm not only an engineer and a chemistry teacher, and I'm also a math teacher, so yeah, get used to it. All right, so we go plug and chug, right? We plug in our quantities. All right, well, our pressure was 0.813 atmospheres. Our volume was 2.15 liters. Our constant, 0.821. Okay, and then our temperature 303. This is going to give us our moles. All right, so we've got 0.00703 moles of nitrogen. All right, yeah, simple as that. So butane, C4H10, okay, commonly found in lighters, okay, is used to fuel, as fuel as also as barbecues, and as an aerosol propellant. That's why, like, when you have hairspray, it says, like, do not use near open flame, and then if you put a lighter in front of it and press down, it's going like a torch. That is not, well, it's normally got alcohol in it too, which is also highly flammable, but the propellant is also lighting on fire. I find it funny that they say butane, as far as barbecues, because I know around in Northwest Ohio we actually use propane, and that's what we also use to, for our heating our homes, or at least I do, where I look out back and I see soybeans this year, but it was corn last year. All right, so if you have 108 milliliters of butane at 715 millimeters of mercury at 25 degrees C, what is the mass in grams? We have three variables. Yes. We have three variables. So what are we looking for? All right. Okay, we know that we have a pressure of 715 millimeters of mercury. So we know immediately what constant we're going to go to. We're going to go to the 62.4 liters of millimeters per mercury, because, why do the conversion if you don't have to? We've got two constants that we can work with. We have a volume of 108 milliliters, 4.108 liters. Great. And then we have that temperature. They gave us that temperature, 25 degrees Celsius at 273, 298 Kelvin. All right. We're searching for amounts, quantities, moles. So let's find the moles. All right. So if we rearrange the ideal gas law, rearrange the formula for the ideal gas law. All right, so we've got PV equals nRT. Again, we're just going to divide both sides by RT. The right side, RT will cancel out, leaving it with N equals PV over RT. All right, now we've got to figure out the moles of butane and create that into molar mass. All right, so, all right, if we look at this, we've got our 715 times 0.108 over 62.4 times 298. That's going to give us our answer in moles. Okay, well, that 0.00415 moles, that doesn't necessarily tell us the grams until we go that one step further. Well, how do we figure out how many moles or how many grams are in a mole of butane? Well, we've got to go back to our periodic table, right? So we find out the mass of carbon, and whatever the mass of carbon is, it was approximately 12, okay, which would give us 48. And then we've got the mass of hydrogen, which is approximately 1, so 48 plus 10, right, gives us 58 or 58.12. All right, we then know that we have the amount of moles that we need. We multiply that by the 58.12. So in this calculation, the mass in grams that we have of butane is 0.241 grams of butane. None of this is overly complicated, just a matter of setting it up, organization, rearranging the equation, and then finally plugging and chugging. Another use of ideal gas law is to determine the molar mass of a gas. So dividing the mass of the gas by the by the moles of the gas gives the molar mass of the gas. Given the mass in grams of the gas, we can calculate the number of moles. So it's just the exact opposite of what we just did, okay? So organize, rearrange, plug and chug. All right, so what is the molar mass in grams per mole of a 3.16 gram sample of a gas at 0.75 atmospheres at 45 degrees Celsius that occupies a volume of 2.05 liters? All right, well, okay, we've got moles, okay, or we got grams of a gas. We've got the atmosphere, we've got temperature, we have volume. Definitely ideal gas laws. We can work with this. All right, so 0.75, 2.05. We have the mass, but we're still looking for the moles. We've got our constant. Remember, we're using the atmospheric constant because we're dealing with atmospheres over here. And then our conversion, 273 plus 45, 318 in Kelvin. So now we rearrange it. Remember, we're looking for moles. All right, so we rearranged it. All right, so we say that 0.75 times 2.05 time, over 0.0821 times 318, that's going to give us moles, right? We found our moles. 0.0589 moles, all right? Well, we have a mass, right? So, all right. And see at the top, it says, what is the molar mass in grams per mole of a 3.16 gram sample of gas at 0.75 atmosphere, 45 degrees C, that occupies? Okay, so we simply then say, all right, we've got 3.16 grams. We divide it by the number of moles, right? Mass, okay, that'll give us our molar mass. So we have 53.7 grams per mole, all right? 53.7 grams per mole, because we got our mass in grams over our moles. All right, that's it. Just like that, simple as that. Remember, organize, rearrange, plug and chug. All right. Now, the details that we need to look at, though, is it, what are we looking for? Is it STP? Are we just dealing with temperature and volume, or temperature and pressure, or volume and temperature? Okay, these are all interrelated. So we just have to be careful of what are they asking for, and then what's the appropriate formula to use. Okay? All right, hope this is all making sense.